Second presentation given online by Takahide Mizuno from the Japan Aerospace Exploration Agency from Japan. Deep Space Synchronous 2 a laser ranging experiment using the LIDAR on board Hayabusa2.
Okay, can you hear my voice?
Yes.
Oh, thank you. Thank you, Chairman. I will talk about the experiments conducted by Asteroid Explorer Hayabusa2 on its return to Earth in 2020. Please note that the results of the experiment are currently under review for publication, so the presentation will be limited. First of all, let me introduce the Hayabusa2 mission. Hayabusa2 was launched in December 2014 and arrived at the asteroid Ryugu in 2018 after an Earth swing-by maneuver in 2015. At Ryugu, Hayabusa2 mapped the asteroid with the laser ultimate LIDAR and also released two rovers, Minerva and Mascot, to observe its surface. In addition, the cratering experiment with the impactor was conducted, and samples were successfully collected by two touchdowns. It returned to Earth in December 2020 and successfully re-entered the capsule to bring back a 5.4 gram sample of Ryugu. Hayabusa2 is now cruising to the next asteroid using excess stellar gas. The experiment reported today was conducted after Hayabusa2's re-entry of the capsule to Earth in December 2020. This figure shows Hayabusa2. This figure shows Hayabusa2's inserting the capsule into its re-entry orbit to the Earth, and then releasing from the Earth. The experiment conducted approximately 2 weeks, starting 2 days after the capsule's re-entry. The distance ranged from several hundred thousand to 6.6 million kilometers. Ground stations participating were Kogane in Japan, Mount Stromlo, Australia, Grasse, France, and Wetzel, Germany. Hayabusa2's LIDAR has a synchronous optical transponder function and returns a response pulse when it detects a laser pulse from a ground station. In this experiment, the Côte d'Azur observatory in France detected the laser pulse from Hayabusa2 and successfully linked the laser at the longest distance of 6.46 million kilometers. Next, I will introduce LIDAR on board Hayabusa2. Preliminary rule of Hayabusa2's LIDAR is laser altimeter for navigation. It has a wide dynamic range that can measure albedo from 6 to 10% target at distances from 30 meters to 25 kilometers. And it's lightweight at 3.52 kilograms. By the way, the laser is a passive Q switch ND YAG laser. In addition to ranging function as a navigation device, it has a synchronous optical transponder function. The transponder function uses an internal clock to measure the time between reception of the laser pulse and the laser firing, and downlinks the time via microwave telemetry. Using this transponder function, we aim at a synchronous two-way laser link. In fact, we tried the laser link experiment in 2015. In 2015, Hayabusa2 approached to the for the Earth swingby. On this occasion, we attempted laser link with the cooperation of the Kogane station in Japan and the Mount Stromlo station in Australia. This experiment successfully detected an uplink from Mount Stromlo to the onboard LIDAR. Figure 3, I'm sorry. Figure 3 shows the result of spiral scanning of the spacecraft attitude and measuring the LIDAR bore sight direction. The bright yellow area is the LIDAR bore sight direction. Figure 7 shows the result of measuring the uplink repetition period from the Mount Stromlo station using the onboard counter. The result can be used calibration of the onboard clock. However, in this experiment, we could not detect any downlink from the Hayabusa2. In this page, I have organized the difficulties of this experiment. The first is the large jitter contained in the laser firing time of LIDAR. It means the response time of the transponder has large jitter. This is because the laser uses a passive Q switch, which has a jitter of about 300 nanoseconds at 1 sigma. Therefore, if the ranging gate is set to 1 microsecond or less, the signal may not enter the gate. However, the response time is downlinked by microwave telemetry, so we can cancel the jitter by post processing. Second, the repetition rate of the transponder is 2 seconds. This means that even if the laser is uplink from the ground at the high repetition rate, the response pulse is returned only once every 2 seconds. Third, Hayabusa2 was visible only during the daytime. I'm sure you are aware of the difficulty of the daytime measurement. And unfortunately, the orbit during the experiment had a separation angle of only separation angle from the sun only about 30 degrees between Hayabusa2 and the sun. Due to these three factors, the signal timing in the ranging gate is a jitter of most of the signal in the gate is noise. In addition to these, there is a difficulty of the long TOF, time of flight time. Usually the TOF in low Earth orbit is on the order of milliseconds. But in this experiment, it's several tens of seconds. To overcome these difficulties, we conducted a preliminary experiment using the engineering model of LIDAR. On the left is the device simulating the ground station, considering of a laser diode to simulate a simple uplink, and SPAT to simulate a receiver here. To simulate actual operation, the uplink was 10 Hz and the downlink was 0.5 Hz. This oscilloscope waveform shows the timing relationship between the return pulse from laser, pulse from LIDAR and the ranging gate. The oscilloscope triggered by the return pulse. And the ranging gate is 2 microseconds. You can see the large jitter. This upper figure shows the detection timing within the ranging gate, including dark. Dark means noise of the diagram of the APD. The horizontal axis is the uplink shot number and the uplink shot number. And the vertical axis is the timing within the signal's gate. The one count means 0.25 nanosecond. The gate length is 8 microseconds. The data sequence can be seen at count 32,000, which is in count when no data is detected. The left graph is with LIDAR signal, and the right graph is without the LIDAR signal. But we cannot find any difference between the left and right graphs, except that the right side has slightly less data. It is necessary to distinguish which is the LIDAR signal from the graph on the left. By the way, SPAT dark rate is about 120 kilohertz.
We are running out of time. How much more slides do you have?
4. I'm higher. The graph below the histogram, the number of data are integrated over an interval of 2 seconds. By using the feature of 0.5 Hz transponder given in the second difficulty. The data with LIDAR signal shows the peak at the intervals of 1 second. But the dark-only graph does not have this feature. This is what we see when we extract data using this feature. The orange and green dots represent the LIDAR signal. In the LIDAR signal, we can see how the clock on the ground station side and the LIDAR side are shifted. So thus the difficulty can be overcome as follows. Large jitter can be overcome by post-processing with telemetry. For low repetition rate, this feature can be used to find the signal. Daytime darkness can be overcome by ground station experience. Here are the results obtained on December 9, 1 million kilometers. On the left are the uplink from the Gokane and Mount Strom station received by LIDAR. From this figure, we can see the 10 Hz and 170 Hz pulse interval. We use the interval to calculate the LIDAR clock. The upper right graph shows the data in the range gate of the glass station. The raw data is shown in the lower left for reference, but it has almost no characteristics. But bottom right is the histogram integrated every 2 seconds, showing a peak at the interval of 1 or 2 seconds, as in the preliminary test with the engineering model. The upper right graph is the result of the data extraction using feature, and shows the clear chunk of data around minus 0.5 microsecond. This is the downlink signal detected by the glass station. So let's summarize my result. We successfully completed a two-way laser ranging experiment between Hayabusa2 and Courde d'Azur observatory in December 2020. The maximum distance was 6.46 million kilometers. We will not go into details because I have to hurry up. So laser ranging experiment with preliminary probes are late, and as far as I know, there are only the following 7 cases. Hayabusa2 is the first successful example of the synchronous two-way ranging. Thank you so much for your kind attention.
Thank you, Takahide-san, for the presentation and also for the nice results. However, you were heavily over time, so we have to skip the questions and keep on with the next presenter.
Okay, thank you very much.